Hi everyone. In the last video, I derived this differential equation right here, and what it does is it describes the equations of motion for a simple pendulum. And now what I'm actually going to do is go through and solve the differential equation. Now I will note one thing. This sine theta term right here makes this equation very, very difficult to solve. And so for this example at least, I'm actually going to be making a simplification here and then using that simplification to derive a equation for theta as a function of time using a bit of an approximation. So I'm going to erase this, but I am going to keep this equation down here. And the approximation that I'm going to make, because the sine theta is so pesky, is we're actually going to approximate sine theta to be theta. Now, why exactly can we do this, and in what situations can we? So the situations that you can use this in is if theta is very small. I'm going to be talking about why that is and actually deriving why. So let's actually think of a graph of sine of theta, right? This is the theta axis, this is the sine of theta axis, and what you're going to get is a graph that looks sort of like this, just a sine wave, right? Now, if you notice here, this is theta equals 0. And if you plot the graph of f of theta is just equal to theta, you'll see that near 0, kind of in this region right here, theta and sine of theta are very, very similar in value. And so that's kind of the approximation we can make. Now, the actual reason, and this is what will be on the handwritten notes that I've released, is that basically, if you've ever taken a Calculus 1 class, you'll have learned about tangent line approximations to functions. So you find the slope of the tangent line, basically values that are right here about. You can approximate the function values with the tangent line. Now, it's the same thing for sine theta. The derivative of sine theta at theta equals 0 is just, well, the derivative of sine theta is cosine, so it's just cosine of 0 degrees, which is equal to 1. And so that means the slope of the line is going to be 1. And so your line is just going to be f of theta is equal to your slope 1 times theta, and that's just theta. And so for those values where theta is very close to 0, you can just approximate sine theta to be theta. There's a more detailed explanation in my written notes, but that's basically the gist of it. So I'm going to take this equation, I'm going to rewrite it with sine of theta as just theta. So our new differential equation is MGL, negative MGL, times theta is equal to ML squared theta double dot. And I can even simplify this more. As you'll notice, both sides have a mass term. You can just divide by that on both sides and cancel it out. Then you can divide by L squared on both sides, and you'll get negative G over L, because you have one L on top, L squared on the bottom. It cancels out, so you should have one on the bottom. Negative G over L times theta is equal to theta double dot. And this differential equation is way easier to solve. In fact, we're going to solve it right now. You'll notice, and this is also something you'll notice if you've ever taken a Calculus 1 class before, recall sine of theta. The derivative of sine of theta is equal to cosine of theta, and the derivative of cosine of theta is equal to negative sine of theta. And so we can rewrite this as the second derivative of sine theta with respect to theta is equal to negative sine theta. Now, another thing is, and so that's already really close here, but we have this g over L term here, right? Another thing is that when you take the derivative of the function, because of the chain rule, let's say I had the derivative with respect to theta of, for example, sine of 2 theta, that would be 2 times cosine of 2 theta, because you multiply it by the derivative of the inside here with respect to theta. The derivative with respect to theta of 2 theta is just equal to 2. And so it follows that the second derivative of sine of something theta, let's just say that something is equal to 2 again, so sine of 2 theta, you're going to multiply it by 2 once when you take the first derivative, and you're going to multiply it by 2 a second time when you take the second derivative. And so that'll be negative 4 times sine of 2 theta. Now we have all the tools we need to solve this differential equation. Recall that the differential equation we were trying to solve was negative g over L times theta is equal to theta double dot. I'll just rewrite it this way. It was this. Notice how this isn't squared. We actually want to take the square root of this, and that's going to be what's inside the sine of theta term. The solution to this differential equation is theta of t is equal to a, where a is the amplitude of our wave, times sine of the square root of g over L times t. And that's the solution to our differential equation. That is the equation of motion that describes our pendulum system. So how do we know that this is correct or not, right? Let's plug it in to this differential equation right here and see if it is a true solution. So if we take theta dot, which is the derivative of this with respect to time, we multiply this out, so we have a times the square root of g over L times the cosine of root g over L times t. And then if we take the derivative again with respect to time, so theta double dot now, derivative of cosine is negative sine, so we pull a negative out here. We have our amplitude. If we multiply this by root g over L again, we have a square root times the square root, and those cancel out. And so this is just going to be ordinary g over L. And this is sine of root g over L times t. And if you'll notice, we have this term here, a times sine root of g over L times t. That is our original theta of t. And so we could then rewrite this equation here as theta double dot equals negative g over L times theta. And so that shows that our function was a solution to the differential equation. And so, just for one last time, I will write it again. Our solution to the differential equation is theta of t is equal to negative a sine. Ooh, I'm actually going to write that over here. I don't have room. Theta of t is equal to negative a sine times root g over L times t. Oh, not the period, the time. And that's our solution to the differential equation. Now, as for the significance that that has, that means that our pendulum from earlier, if we plot this angle theta with the vertical with respect to time, this is the function that's going to describe it. What does this function look like? Well, it's just a sine wave. So it'll look something like this. And what does that mean? It keeps cycling and cycling. Well, for a pendulum, it means that as time goes on, this pendulum will swing back and forth. One time it'll be over here, and another time it'll be over here. It'll just keep swinging back and forth, and that's what this equation tells us about how the pendulum system behaves. And that's really it. Once again, I'll further restate this. I'm going to be posting written notes in the comments. If they're not in the comments or the description, then I'll post them on a community post, but they will be somewhere. And when I do post them, I'll leave a comment under both of these videos. And also, if you have any questions, comments, concerns, any of that, feel free to ask them in the comments. But that's basically it. Thank you for watching.